we have before us a second-order differential equation, which is actually easier to solve than a first-order differential. We'll have to find something to replace these differentials. We'll call it m squared plus 4, and then we'll just call this an m, plus 8, and then we'll just call this a 1. Now, we'll try to solve this for when x equals 0, and we'll call this the homogeneous auxiliary equation. Now we could just plug this into a calculator, but I think completing the square is pretty cool. So if we had an m plus 2 and we squared that, then what we would get is m squared plus 4m plus 4. And we're missing some 4 over here, so we'll do that. And essentially we get this equation right here. Well, let's write that m plus 2 squared is equal to negative 4. And then we'll square root both sides. So we'll have m plus 2 is equal to the square root of negative 4 is going to be 2i, but we'll have a plus or minus in front of it. And then we know that m would be equal to negative 2 plus or minus 2i. So we have our answer for m. What we're looking for is a general solution to this equation, which is going to be y equals yh plus y particular. This is a homogeneous solution here, which is equal to 0, and then the particular, which is when it equals any other x. So we'll just say that the homogeneous solution, we need to figure out that one first. That's what we're looking at over here. So we got c1 y1 plus c2 y2. We know we have two solutions because it's a second order over here. In fact, we see we have two m's. So then we have y1 is equal to, and a y2 is equal to, we could put e to the m1x and e to the m2x. This is going to be the two solutions that we would have. So if we plug in these m's, we have something like e negative 2 plus or minus, well actually this is just the plus side over here, 2i, and this is times x. Then on the bottom we have negative 2 minus 2i with the x. This can be simplified into e to negative 2, e to the 2ix. On the bottom we have negative 2e, and this will be the negative version, like this. And we can also use Euler's formula, which tells us that cosine theta plus I sine theta works for this equation here. We could say e to negative 2, and then we'll have to throw in a cosine of 2x plus I sine of 2x. Same thing here. But here we have a negative version, so we'll put negative 2x and then plus I sine negative 2x. We'll simplify this bottom part one more time because we know that the cosine of negative 2x is the same as the positive 2x. And this will just turn everything negative on this side. Negative I sine 2x. Now let's plug y1 and y2 into this equation here. The homogeneous equation will be c1 times e to the negative 2. We have the cosine 2x plus I sine 2x. And there's just so many parentheses here. And then we have plus c2 e to the negative 2 cosine 2x minus I sine 2x. Now we could start finally simplifying this down. We'll pull out the e to the negative 2, and we'll take the c1 plus the c2 with the cosine. So c1 plus c2 along with that cosine of 2x. Then we'll take the c1 minus c2 over here. c1 minus c2. For the sine versions, let's throw the I there as well. The sine of 2x. We have something like that. But this can be simplified one more step by saying e to the negative 2. This is going to turn into a k1 cosine of 2x. And then this will just be the whole thing, including this I, k2 sine of 2x. So now we have the homogeneous solution on the left. But let's try to get the right side, the particular solution. Since we have a 5x over here, we have to assume that we'll have some particular solution that has an x in it. So we'll just say ax. This a will absorb that 5. And then we can just add some constant over there because we don't know about that. So ax plus b. In fact, this makes quite a bit of sense because y equals mx plus b, right? Okay, cool. So now we have to use this equation here that we have, this differential, and we'll take the first derivative. So we'll say y prime is supposed to be equal to just a, and then y double prime is going to be equal to 0. Everything's working out so far. Let's go ahead and plug these into the equation. So I have 0 plus 4a plus 8 times ax plus b, and that's equal to 5x. If we rearrange this equation a little bit, we'll say 4a plus 8ax plus 8b equals 5x, and then we'll put ax plus 4a plus 8b, put that together, that's equal to 5x plus 0. And we can clearly see how these are supposed to match up. In fact, 8ax equals 5x, and 4a plus 8b equals 0. Well, from this we can see that a is supposed to be equal to 5 over 8. And over here we have something like 4a equals negative 8b. We could divide this over and say that negative a over 2 is going to be equal to b. And so we know that b is equal to negative 5 over 16. We can see how the 5 was absorbed into these constants. And we can finally write the equation y is equal to our homogeneous solution here, k1 cosine 2x plus k2 sine of 2x plus the particular solution over here, ax plus b, which we know a to be 5 over 8. Then we have the x plus the b, which is, well, negative 5 over 16. And that's going to be our answer. So, holy smokes.